be a little bit less technical, with a high level, but it's gonna complement very well the previous one. So let's get started. First, I didn't take that picture because that's my first time in Porto. So does this work? Sorry. Okay. So now I get it. Okay. So hi, I'm Miguel. Originally from Colombia, but I come from Germany. I landed yesterday. You're gonna find me mostly in Python-related events, and I work as a senior data scientist for New Yorker, which is not that New Yorker. It's this New Yorker. So you probably know it. It's basically a fashion retailer, and that's what I'm gonna talk to you about. Data science in the fashion industry, in particular demand forecasting. So what are we going to talk today? So we're going to try to build a small system, a demand forecasting system. So the first thing, I'm going to give you some introduction to demand forecasting, and then we're going to talk about what requirements does the system have to have in order to provide good results. Then we're going to take a look at what models we can use to build that system. And finally, I'm going to talk to you about some practical tips. So demand forecasting. What we want to do in demand forecasting is to be able to capture the previous factor that influence the demand, so we can create predictions. If you want to see it as a plot, you can see, like, if you plot the sales or the demand across time, you're gonna see a time series. So the blue is the predicted one. If you want to see it as a table completion problem, you have one column with the date and the other one with the sales up to time t, and you want to complete time t plus 1, t plus 2, up to t plus n. That's like multiple step forecast. What applications do you have for that? Well, if you're a retailer, you want to have long-term forecasts so you can prepare the production for the next year, let's say. You want short-term forecasts for replenishment of the stores that you have, for example, the next couple of weeks. Also, if you have a product that you are not able to sell, you can use forecasts to know, like, well, I'm not gonna be able to sell all the stock for that product, so probably I need to make some discounts. And in general, for general financial planning. We have to take into account some constraints, in particular for the fashion industry. We have a strong relationship between the weather and the clothes. So probably in Porto in summer, you're not going to buy a lot of jackets. But if you're in Berlin, you will do. And weather is quite, say, unpredictable. So recently we have a problem. There's a hot front in Germany, and the jackets are not being sold as expected, for example. There's also external factor that we need to take into account. Fashion is a thing, although not for me, but some people really follow fashion, and they and that can change the sales behavior. So if, for example, one of the Instagram's influencers posts something, you might get some disturbance. You have a lot of products as well, so you need to support that. And let's say, at least for fashion or like affordable fashion, consumers, that means you, are very unfaithful. If you have two products that are similarly priced, very similar products, but with one is like slightly cheaper, you're gonna go for that regardless of the brand. Now, it's not working now. Yeah. So requirements. The systems should support multi-horizon. That means, like, as I mentioned, I need long-term and short-term forecast. That is in particular because in fashion industry, you have manufacturers normally located in other countries like Turkey and India. And there's a time between the production starts and it's like delivered to the warehouse. And we need to predict the sales up to 1 year or more in advance. But also we need the short-term forecast for replenishment. Seasonality, as I mentioned, products can be very seasonal. So in the left side, you see, say, those jackets I mentioned. So those are winter items, and then you have a spike in the cold months. But you also have products with no clear seasonality, maybe a trend, but no clear seasonality. And we need to capture somehow the exogenous variables that influence the demand. Now, it's very hard to sort of collect all of those variables. And also, this is not exhaustive. But what makes this especially difficult is that they can be correlated. So it's really hard to measure the influence of all the variables. So one might influence the other, and they are not the same across time. So in certain years, some of these variables can have more influence than in other years. Now let's go more like machine learning, model, data science part. I hope you're not bored by now. So probably before jumping into that, we have some requirements that I mentioned. And what are the implications? Well, we have multiple products. We need to support them multiple time series because each of those products is basically one time series of the sales. Different product life cycles, we need to support highly non-stationary time series, meaning all the series I'll show you, like similar with season, with trend, etc., etc. And we have to be flexible regarding the horizon. Now, what models do we have? We have traditional time series models, which were developed in the 1970s or something. We have, for some of you, ancient machine learning models, like linear regression, and also the more recent, like gradient boosted trees that you learned a lot in the previous talk. And the new cool kid in the block, deep learning. This is a scorecard that we're gonna try to fill out with the sort of how a particular model allows to, or it's like fits our requirements. And let's start with a traditional time series model. This is the cool map slide I needed to put, so the science part. I'm not gonna go into detail, but in a nutshell, the traditional time series model used previous data, basically the previous sales and the previous error to be able to predict the future, the target variable. Normally what you do is that you plot the time series, then you do some transformation, you take finite difference to remove the trend, and then you plot the autocorrelation, partial autocorrelation, you run some tests, which are really weird and I don't really understand them. Or you can use automated tools like in Python and R, you can just call auto and they will give you some parameters. And then you plug those parameters and then you got the forecast. These are the I think monthly sales of cars in Australia from something 1966. That's how new the model is. Now, this is okay. It is easy to use. However, that's how real sales look like in the real world, and they are nothing like traditional time series that you can see in the literature. So it's not so good for this type of highly non-stationary phenomena. Also, if you have multiple products, like we're talking about thousands of products, you will need to fit one of these models, either manually or automatically, which might not work very well. You will need to fit one per each product, which is kind of hard to maintain and to measure the performance. Now let's, so in conclusion, not so good. Probably we're gonna skip it. We're not gonna use it in our forecasting system. Now machine learning, you probably already very familiar with this type of models. The key thing here, which the previous speaker said, is the features. And you have basically three big steps. One is like obtaining the source data, and you have sales data, product attributes like color, mostly categorical things, time related, and location like the holiday and weather information if you can put it in. Then you need to encode it. Well, one, you need to extract it, which might be really hard. In particular, if you work on those companies with Asian ERP systems, it's very tough. You know that 80% of the time on data wrangling and 20% modeling, that's how it is. And then you need to encode it because at the end of the day, machine learning algorithms, they only understand numbers. So you have the more traditional numerical encoding, like one-hot encoding and feature hashing for categorical variables. There are some extensions. And recently, entity embeddings. I will describe them soon. So this is a small sample of taking a table with some products and some sales and transforming it into something that the machine can understand. You can see there's a column with when we extract the month, the week of the year. We also encoded the price into some discrete bins, and the color we encoded as one-hot encoding. The models that you have available, this is not exhaustive. You have the linear regression and super vector regression, which are the very traditional, and also you have the tree-based models that we learned. Machine learning is very good. It helps you can put all the products at once if you want. It doesn't make any assumption from the distribution of the demand or the sales, for example. The problem is time consuming. Feature engineering is king, and you have to. That's a very important takeaway. Now the cool kid, deep learning. You have the multi-layer perceptron, and then you also have like the variation of recurrent neural nets. Honestly, we tried some of them, and in my team, we had the same experience as you. So not really that good for tabular data, which is what we have when we're working with demand forecasting. However, I wanted to mention that you could learn categorical features using entity embeddings. This paper comes from the Kaggle competition, the Rosman Kaggle competition, and they basically learn representation using a matrix. And each of the rows of the matrix is a category, and the neural net learns both the categorical variable representation and try to predict the cells at the same time. And on the right, you can see a TSNE plot of the representation of the cities in 2D, and they're like more or less, they have a similar layout as the geographical layout in Germany. So deep learning, very flexible. Theoretically, you can use it to learn new features and then do transfer learning. In practice, I haven't seen any paper that do transfer learning in using tabular data. If you know one, please let me know, but I haven't seen that. And you still need to do feature engineering. Like that's not like you take the table, the CSV, and you don't do neural net, read CSV, and predict. That doesn't exist. And it's really hard to interpret the model, like compared to other models like machine learning or the traditional time series. The summary, I think machine learning, and in particular gradient boosted trees, is the way to go. Probably deep learning will get there eventually with new models, but so far, I would say start simple and then try deep learning if your approach doesn't work, but don't expect like a super performance in tabular data. So now some tips and some practice from the practice area. So evaluation of metrics, this is very important. You need to pick the evaluation that sort of matches your problem. In sales forecasting, for example, maybe we want to use MSLE or something similar. Other people use a quantile loss because that gives a confidence interval. And if you can explain what a confidence interval is to the business, it's very useful. Another thing that you said about the cross-validation is very important. So on the left, you're gonna see like the typical cross-validation from time series. And then all of on the x-axis, you have kind of like the time. The blue part of that is the training data. And on the y is like all the different runs of the cross-validation, the faults, so to say. So you train on the blue part and try to predict on the red one, and if you want to predict one instead. The takeaway, you can only use data from that blue part in order to do the prediction. So if you say you want to calculate the mean of one variable, you cannot do it on the whole data set, but only on that blue part. Otherwise, you're gonna leak data. And that will give you sort of like a good model, but it's not real because you're cheating. Don't cheat. on the right graph, this is coming from one of our projects. Well, you also have the issue that some products might have different historicity. So imagine you have a product that only was sold in 2012 or 2015. You're not going to have enough time to train the whole model on it. Then when you can do kind of like a sliding windows approach, and you have to make sure that if you train on a product, you have to evaluate in a product that also has enough data in the training set. Otherwise, your cross-validation score are going to be really bad because, say, you only train the modeling with 2 samples and try to predict the whole historicity of a product, it's going to be really bad. So cross-validation, very important. Some useful predictors that we have found is adding a trend, basically a counter. It can be a relative counter or the lifetime. It's nothing out of the blue, just add a number that counts the number of weeks up to the one. Incredibly works very well, at least in sales. Put in seasonal variable depending on the time, sort of like the time resolutions. If you're working at time resolution, you probably want to encode the days. Say you have sales per day, then you want to encode that time as a number. In this case, one-hot encoding. Another thing is intervention variables. This is a term coming from the traditional time series world. And the idea is that if you're able to capture things like promotions or competition or marketing, say you have data about if a shirt was put on the web page, you can mark it with a Boolean variable and then keep it in one while that was on, say that t-shirt was on the website, and remove it when they remove it from the website. Generally, intervention variables are hard to capture, and even if you can capture them, they are really hard to put in the future because you don't know. Maybe they will be activated or not. And I think that's it. So, summary. Demand forecasting in particular in the fashion industry is very challenging because you have a lot of external factors and they are really hard to capture. Use gradient boost. Feature engineering is important, so you can spend hours and hours reading about models, but I recommend you read how to wrangle data, learn how to do feature encoding. That's way more important than sometimes applying a model. And right now with the APIs, it's basically a couple of lines. The value of data science is not on the models, it's on the feature engineering, on the expert knowledge. And you have to avoid feature leakage or data leakage using, like, be a good boy and use cross-validation for time series, a very robust cross-validation, sorry. And the typical business match, you have to match your metric with your business and whatnot. You all know that. You never do it anyway, so I'm not gonna insist on that point. And some references that you're gonna find on the slides, some credits, and yeah, that's it. Thank you.